All right, welcome back to lecture 5, DS 4420. This is Professor Wu. Today we're going to start going over reviewing some probability notations. So let's get started. Probability mass or density function, also known as PDF, probability density function, or PMF. Okay, right? They are ways, functions of telling you the likelihood of a certain event. Now, the notations are different. The symbol for x and x have different meanings in probability versus linear algebra. In linear algebra, remember I was saying that x right here is a vector. It's a variable. And capital X is a matrix or vectors of vectors. However, in probability, there's an extra dimension you need to think of, that x is one or multiple events that happen. So they're different. Like x is a vector, x here is the event that happened, past tense. Now x is the random event with many possible outcomes. So this is the event and this is what actually happened. Okay? So the notation, you want to make sure, depending on the context, you have the notation correct. We use the capital P or lowercase p to represent the probability function. For example, maybe you will see P of x is 25. That means the probability that x would happen is 25%. Or you can see that the probability of the event turn out to be small x. So this is what the event is, and this is the result of the event. So if out of this event x happened is 0.25. So these two are actually the same, right? So it's saying that x happened. Here is also saying that x happened. Okay. Now 0.25 out of 100%, which is 1. So 100% will be getting a value of 1. Now, P of x is a function where you plug in an event you care about and it outputs the probability. Okay? The probability mass or density function, PMF, PDF, is the function that does this, where you plug something in, it tells you the probability. Okay? The difference between PMF and PDF is that PMF are discrete data and PDF are continuous data. So probability mass is for. So let's look at an example of probability PMF. All right. So over here, let's say you roll the die 5 times, and you got 2 1s, 1 3, and 4 4. These are discrete numbers, right? Where you know that from this, the probability you're getting a 1 is 2 out of 5. Probability you're getting a 2 is 0 because it didn't happen. Probability you're getting a 3 is 1 out of 5. Probability of 4 is 2 out of 5. Probability of 5 is 0 because it didn't happen. Probability of 6 is 0. So based on this data, these are the probabilities that we can calculate. Essentially, out of 5 times, one happened twice, right? So it'd be 2 out of 5, right? That's how we calculate the probability, right? Or you can write it the probability that one happened, or you can just write P of 1 is 2 5. So these two notations are basically the same thing. So from here, you can see that PMF can be obtained simply by counting. So you just count them, right? So over here, you can look at the histogram, and the histogram tells you that, well, the probability of nuclear is 2.5, 2.5 is 0.5. Okay, so from the plot, we can also tell the probability. Or if we have the function itself, right? Now, an example of probability density function is, for example, this line. So you have a probability all the way from 0 to 2, right? So that it will be an equation, and then it will be between 0 and 2. Now, with probability density function, when you want to calculate the area, one, like for example, if you want to find a probability between 1 and 2, so you need the area out of the total. So you will need to essentially integrate. between 1 and 2. Remember, integration gives you the area under the curve. So if the total area is the entire triangle, therefore this portion will essentially tell you the probability um, of a happening between 1 and 2. Okay, so at this point, you want to pause the video, see if you can find the probability of 1, which is the integral from 1 to 1 of this. And you want to find the probability between 0 and 1. So what's this part? And the probability from 0 to 2, right? See if you can take the integral of this. And we'll move on. Hopefully you were able to get the right answers. So these are the answers for all three scenarios. The code to do this, because integration is not fun. Like this is a very simple integral, but if it gets complicated, then it's not easy to do. So with Python, what we can do is we can call the quad function. So if we define a function as 0.5 times x, which is this, right? Then you can just put the function inside the quad, and then you say I want to integrate between 0 and 1, which is integrate from 0 and 1, right? Yeah, like this. So this automatically calculates the area. And notice how it's the same as when you do it by hand. Now, why do we need probability density, probability mass function? That's because life is uncertain. Like who's going to win the World Cup? Which company you're going to work for? Are you going to be successful in life? None of these are certain. They're all like probabilistic. Therefore, nobody can predict the future. But if you have an accurate PDF for all the possible outcomes, well, it will allow you to make decisions based on informed likelihood, or if you know how to pick the right stocks based on probability, or just make generally good life choices. So much of data science is really to understand and model this uncertainty. And that's why understanding and the ability to manipulate this data in terms of probability is so important. Okay, so let's familiarize ourselves with these concepts. So the first thing we're going to learn is multivariate. We're not just going to deal with one variables. When we have multiple variables, we simply have more variables in here. So now it's a function of two variables, functions of three. But in general, we like to write functions of 1, 2, 3, just because we could have a lot of them. And we can then represent x as a vector of random variables. Okay, so here, whenever we see p of x, right, we can also view this as p of x1, x2, x3, so on and so forth. Okay. Now, when we have multiple of them together, we call these the joint distribution. Joint distribution, and this is saying that what is the probability of x and y happening? So when you see this, this is saying what is the whatever this function returns is telling you the probability that x and y happen. So, like I said, these are called joint distribution because you're joining multiple variables together. Now, the notion p of x can alternatively be written as this is p of x, or you can write p of x happen and y happen. Another symbol for and is this. Okay, this is called the intersection. So if you have a and b, the intersection of probability of a and b happening. Okay? So now, the alternative to an and is a or. So this symbol is a union symbol, which is saying the probability that x happen or y happen. Okay, so that's what these mathematical symbols mean. So the or logic, if you want to find the probability x or y, it's equal to the probability x plus probability y minus this. You can kind of see this through a Venn diagram. If you have the area of the red and the area of the blue, right? If you were to add the area of the red and blue together, you will essentially have an extra overlap. So you have to subtract probability x and y, hence removing the overlap to have the area of the total. So that's how the OR logic works. If you want x happen or y happens. Now, if we want to understand joint distribution, we can view it as a table. So over here is the probability of x equals to 0 and y equals to 0. Well, here's the probability of x equals to 1 and y equals to 0. Okay? Right? So you would write it this way. So 0, 0 would be this one. 0, 0. Right? Or another one, what is probability of 1, 1? Would be 1, 1. 1, 1. Or, yeah, 1, 1, which is 0. 0.1. And the probability of 1, 0, 1, 0, which is 1, no, 1, no, probability of 1, 0 is this one. Oh, this is a typo. Probability of 1, 0 should be 0. 0.2. Yeah, like this. Okay? All right. So when you have a joint distribution like this, like joint together, well, a common question is, if we know the joint, does that imply that we can still have access to the individual probability? If we have P of X and Y, does that mean we still have P of X or P of Y? Or is that information lost? Okay. Yes, the answer is yes. You can still get the individual probability back. And this is called marginalization. Like if we use the table, we can see that we can still find a probability of individual variables by realizing here, let's look at this table. If you want to find the probability of x, right? Well, it will simply be the probability of x equals to 0 and y equals to 0 plus the probability of 0 and y equals to 1. The probability of 0 and y equals to 2. So basically, it's the entire column. So if you want a probability of x, you simply add all the possible combinations together, right? So I said it here. You basically, if you want to find probability y equals to 0, you will loop through x. So in this particular example, if you want to find a probability y equals to 0, you will loop through every single possible x options and add them together. So visually, if you want a probability of x, you just sum the entire column, right? You want a probability of y equals to 1, well, you just sum the whole thing. So it's 0.6. So that's what marginalization means. And in terms of equation, if you want to find a probability of x, right, you keep x constant and you just sum up all the possible y. Right? If you want all the y, then you keep y constant, you sum up all the x. So that's the meaning of this equation. This is marginalization, which is easier to see visually. You want the probability of something, you sum up the entire thing. All right, notice you're looping through y equals to 0, y equals to 1, y equals to 2. So like here, right? You're looping through y equals all the y's while keeping x the same. So that's marginalization. Now, this is when you have a nice discrete table like this. However, when you don't have a discrete table, you have a continuous table, it becomes an integration. So you need to, instead of sum over y, you need to integrate over y while keeping x as constant. Okay? So over here is another example of marginalization. If we want probability x equals to 0, it would be this here, right? 0.0 plus 0.5 plus 0.1. And if you want probability y is equal to 0, it's just 0.2. Okay. Now, if you have higher dimension ones, you will have to sum them up more. Like if you want to find probability x equals to something, you keep x constant and you sum every possible y and x. And you will have to take the integral for these cases. So, want to pause the video and see if you can calculate these. Okay, so this is union, this is or, and or. This is and or. So give this a try. The answers are in this page. When you're home, you want to make sure you take a look and go through the answers. Okay, so the next thing is the concept of conditional probability, and that's probability given some conditions. Let's look at two situations. Situation number one is the probability that you will have a good date tonight. Okay? And situation number two is the probability that you'll have a good date tonight, given that you'll be talking about your ex the whole time. Now, from this example, you can see that the probability drastically, and I mean drastically, change given some other information, right? Given that you'll be doing A, B, or C, the probability changes. So, how do you model this change in probability? It's called conditional. So, given some condition, then what is the probability? And the way we will write this probability is this notation. This is saying this bar here is saying that the probability of x given that y happened, or the probability of y given. So the one in the back is the given. Okay. Of course, you can always write probability x given y and z. Right. You can have given multiple informations. So here we'll just work on one. Given one information. Okay. So so over here, probability you have a good date given, right? This symbol is given that you talk about your ex. The equation for conditional probability is the probability of x given y is the probability of x and y divided by y. Now, if you just look at this is not easy to remember. But if you understand the concept of conditional, right, you can actually rederive this equation yourself. So, so conditional probability. The equation for conditional probability, which is this I just showed you, is not accidental. Okay? And it has a very, very logical reason, as long as you understand what conditioning means. So, given the probability shown on the right, if no additional information is given, then you have six possible outcomes, right? You have six of them. So, nothing is told to you, then you have six of them, right? So, these are the six possible outcomes. Okay? Now, the total probability of everything that could happen would be the summation of all the probability. So if you have the entire thing, if you sum up all the probability, right, that should equal to one. So this represent one currently represent everything that could possibly happen. Six events. Okay? So the total probability is the summation of every possible event. However, if y is equal to 1 is given, this means that you are saying that this doesn't exist. We are already saying that this is now 100% of the probability. Okay? So if this is 100% of the probability, which y equals to 1 is given, right? Then the total probability would be, well, the marginalization would be x equals to 0, y equals to 1, and x equals to 1. So this is now the total probability. And that's the key to remember, right? But when you are given additional information, then the total probability shrinks because other possibilities are no longer possible. Okay? Now, once it shrinks and they ask you, well, if this is the total probability, what is the probability that x is equal to 0, right? Therefore, it's x probability of x equals to 1 and y equals to 1. Divide by the total probability, which is probability of y equals to 1, right? So this is probability of x and y given probability of y. Okay, this is how we got this equation. It's because it's being constrained by probability y is equal to 1. So that's the total. And then the numerator is this one. So you would take this one and divide by the total, right? You take this one, divide by total. That's what we have. So it's probability of x and y, which is this event, right? This event, divided by probability of y, which is the total. So, so this is the logic and understanding of why the conditional probability follows this equation. So, on the exam, you will not have any cheat sheets that you are expected to understand this. But if you understand the logic of what's happening, you should be able to rederive this equation. So the focus is to basically understand that you are constraining the space and then you're picking something within that space. Okay? So here's a good practice, right? You want to pause the video and see if you can do this. Here are the following questions. What is the probability of you having a bad day? How about this? What is the probability of having a bad day given that you talk about your ex the whole time? Okay? So pause the video, see if you can answer this so that you understand the concept of conditional probability. All of these are going to train you to do that. Okay? After you're done, I provide the answer. So double check whether you got it right or not. Okay? Now we're going to move on. Independent variables and how it impacts the joint distribution. Okay? Now, we just talked about this, right? So this is conditional probability. Well, let's do a really quick thing. If this is the conditional, this means that if we move this over there, then the joint must be equal to the product of these two. So the joint must be equal to the two of them multiplied together, right? So this is a joint. And when they're independent, right? What does independent means? When we say two variables, x, y, independent, it means that knowing y give us no information about x. That's what that means. Knowing y give us no information. It doesn't change x at all. So if you know y, like you know that it rained in Thailand, will that change whether the NBA game tonight is going to, like, who's going to win? No, it doesn't really change. Therefore, in those cases, you can actually just get rid of y because knowing y doesn't matter. When you have a independent variable between x, y, then you simply get rid of y, and the equation and definition is that the probability xy is equal to the probability times probability y. Okay? Notice how this and this is the same. And that is how independence came about. The concept that knowing one fact doesn't influence the probability and likelihood of the other fact. And this is saying that if it doesn't affect it, then this probability won't change anyways. You don't need this. And hence, this right here is the definition of independence. Okay? Statistical independence. Okay? Under this condition, we will say that x and y are independent variables. Okay. The next one is called the Bayes rule. The Bayes rule is based on the conditions that we learned, right? So from here we know the definition. We learned the definition of the definition of the conditional probability. You got to go through that logic a couple times, and then we can also move the joint here, right? So this is the joint distribution because I moved that over. Well, if we know that this is the definition of joint, right? That means when we have the definition of a conditional probability, we can put the joint, the definition of the joint here. Okay? Right? Look at this slowly. This is saying, this is right here is the definition of conditional, right? This is a conditional. Now, the joint can be written this way. Probability y and x is equal to probability y given x times probability x. So notice this is backwards to this. So you can write a backwards logic. And therefore it's saying that this is equal to this. Okay? This is called the Bayes rule. And this is, believe it or not, like it looks like a bunch of like algebraic manipulation, but it has very significant implications. And we use Bayes' rule for basically all probabilistic logic, like reasoning, right? So this right here is called the Bayes rule, and yeah, make sure you know it. Right. So I have also provided you a practice to do the Bayes rule. Over here in a neighborhood, if 90% of children are getting sick due to flu, 10% due to measles, the probability of observing a rash given the kid has measles is this, then what is the probability that the kid would develop a rash and a flu, as well as develop a rash and measles? Okay, so these are the questions you want to answer. Use the conditional probability as well as Bayes' rule. You will see why the Bayes' rule is so useful in this particular example. Okay, I also provide the answers, so you have the chance to go over them yourself. Okay, all right. So I hope at this point I have convinced you that if you know the PDF or the PMF, is really, really important, and they're super useful. They're super useful because they allow you to find the conditional, they allow you to find the join, allow you to make good dating decisions if you know the PDF, right? So if you have data, then how do you estimate the PDF? Like, is there a way you can like look at it and see it? And these are the most common approaches, and we're going to go over some of them. And today we're going to look at the easiest one, which is called histogram. Okay. Well, histogram is really easy. You take the data, you count them up, so they're two. So 2 out of 4, that's 2 out of 4 is 50%, right? So 50%. So one would be 50%. Wait, why did I say 25? Anyways, this should be 50%. I think I did something wrong. Two should be 25, 25. Three should be 25. Huh. Maybe I did something wrong here. Interesting. Well, anyways, this is supposed to be 50%. I'm not sure why here. Maybe I wrote the code wrong. But anyways, this is a general idea of how you will write the code. I still don't. I'm looking at the code. I don't see any issues. But well, we'll try it in class. I'll take a look later after. So you want to use his, and you put the data in, and you automatically draw it. Okay. 10 here is telling you that you want to divide it by 10, but there's less than 10. So in this case, it doesn't really matter anyways. Okay. Okay. Did I do? Yeah. So over here, oh, maybe I just did that wrong. Over here, it goes with the count. So it counts twice. So it happened twice. This one happened once. This happened once. So this is the code. Yeah, you want to follow this one for histogram. Okay. And then you have this one, which converts into probability. So it's 50%, 25, 25. So this is the code if you want to represent it in terms of probability. All right. Now, these are simple discrete data, so there's only a couple. But sometimes you have very complicated data that you just, let's say, generate 3,000 of them, and it turns out to look something like this, right? So this, I say I want to divide it into 20 increments, right? And then it shows it. So by looking at the histogram, you can see that the probability between negative zero point 0.5 and zero point 0.5 is very high. These are the highest probability. And you can see that the probability that's beyond 2 and minus 2 gets very, very small. So this allows you to make predictions. If somebody asks you, well, what is the probability that 7 will happen? You can tell them it's basically 0. It's very, very small. And then if the probability, what's the probability here? Well, you can simply count it up. All events here divided by the total. And that will give you the probability. So By looking at this histogram plot, you can very quickly gauge where the data is most likely going to happen and where it's very unlikely going to happen. Okay? So, for this class, you want to go to the course website and you want to find these three data sets. For each one of them, I want you to generate the histogram. Once you generate the histogram, calculate the average. So where's the average point? And then calculate the probability that someone will score higher than 1300. Okay, so that's the first one. You just count them. And then calculate probability, you have to wait more than 3 minutes. So this is the lunch wait time. You have to wait more than that. And calculate probability that someone's younger than you. So you're probably 19 or 20. So this is it. Okay, so that's the end of the day. I hope this wasn't that bad. Will I'll see you next time. Bye.